Okay, it's about 5:02, and I'm going to do a little warm-up beforehand, just to warm myself up as well. It's basically news, but I hope when I start doing it, half of you will know precisely what it's about, and the other half will know by the end. So we'll see what happens. I'm going to start in a very silly way. I've long been an aficionado of animated films, from the early ones done with layers of gels, cell gels, up to modern computer graphics. And I've been to almost every one there is. There was an embarrassing story. Do you remember The Snowman? Beautiful. And for the very first time in animated graphics, they had a thing flying around. Flying through the air? Lovely. And that was really good. The first full feature film to use that technique was done by Disney, called The Borrowers Go Under. In fact, I think an albatross flew two of the little mice down to Australia or something. Does anyone remember that? Well, I wanted to go to that to see it, because it was told to be very good. I couldn't get my kids to go with me, or my wife. So I went along. It was at 6 o'clock, and I joined this queue with all their mums and kids. And to be totally frank, sadly, I don't think I dare do that now. It's a reflection on society. Anyway, I got to the little pay kiosk, and the lady said to me, "Are you sure this is the film you want to see? Because the, quote, adult film isn't till 9 o'clock. Anyway, I did watch it. It was very good. Now, why do I say all of this? If you've seen some of the Pixar films, Toy Story 3 was one of them recently, you will probably know that they tend to have a little pre-film. Have you been to one? Always a short. So I'm going to give you a short. The Pixar ones, because that's where the little lampstand bashes down the eye. Do you remember? Anybody? And just to show I know a little bit about computer graphics, that is a reprise on the very first animated film made by the people that started Pixar, which had a mummy lampstand and a little toddler. Does anyone remember that? Yes, so anyway, that's what it's all about. So I'm going to give you a little mini lecture just before we start the main one. And here is the title. It's Tycho Brahe's Life and Death. If we could have the lights out at the front, perhaps. How many of you know what I'm talking about? Why I'm doing it today? Not that many, actually. All right, you will find out. Just briefly about Tycho Brahe. He was a son of a Danish nobleman. His uncle basically abducted him because he hadn't got a son. He wanted to have an heir, and they came to some agreement about that. But he was very keen on science. He was supposed to go and do things like religion and law at university. Got very fed up with that, did astronomy and things, much better. And in 1572, he observed a supernova, and it was in the constellation Cassiopeia. And he compared his observations with those of someone called Thomas Digges, who was in England, and from the parallax, basically they couldn't see any parallax. The direction of the supernova was exactly the same from both England and Denmark, where it was. This implied it must be a long way away, beyond the moon, and of course in those days the fixed stars weren't meant to change. And in 1573 he wrote a book, De Stella Nova, of the new star, that basically said that these observations contradicted those of Aristotle. He became very famous from this, and that's actually a lovely view of Tycho's supernova today. You cannot see it visually. It was first detected in recent times by our a 218-foot radio telescope at Jodrell Bank as a radio source, and this is a lovely image we have now. Well, the king of Denmark gave him an island called Haven, or Haveen, it's here, between Denmark and Sweden. It's now owned by Sweden. On that island he built, first of all, a castle and an observatory. And this is a Google Earth image. It shows you where the castle was. Most of it's gone. It's building the stones and all this stuff now, I think. And here you'll see is the observatory, which has been restored. And I do want to go there sometime next year. And that's just looking in onto it. You see this rather nice sort of square outline here. And that is a lovely little wood drawing of what it used to look like. And that's the sort of idea. So that was completed in 1580. It's called Uraniborg. Then in 1577 he observed a comet and showed that the comet was a long way away. Because they used to think, didn't they, that comets were noxious vapors floating in the atmosphere. That's just the view you get from Google Earth of the Sternberg, his observatory. which used to look like that. And this is a picture of his giant mural quadrant. In fact, it's not what you'll find. This window, you look through here at a star and you measure its elevation. Notice there's a vernier scale to make very accurate measurements. And notice also a clock, so you could tell when a star went through the meridian. A combination of elevation and knowing the time gives you its position in the sky. In fact, in the original, this is about there. It really ought to be horizontal, so I've just moved it a bit to bring it to the right place. And that's the basic idea. You look due south, you measure the elevation and the sidereal time of a transit, you find out where the star is. And essentially, he made a catalogue of 777 stars, which were an order of magnitude more accurate in their precision than anything that has been done before. And in fact, the catalogue went to over 1,000 stars. And that was used by Brahe in his fantastic star atlas called Uranometrica of 1661. That's a picture of Brahe's atlas. Now, the key thing is that for 20 years he observed the positions of the planets against the fixed stars. And that was a wonderful database of planetary positions. Now, the king who was his mentor or supporter died. His son didn't like Tycho very much, so Tycho got kicked out. He left to Venn. He floated around Europe for a bit. He then became the imperial mathematician to Emperor Rudolf II and was given the choice of castles. I was never offered a castle when I got this job. However, the Astronomer Royal, some years ago, used to have a flat in Herstmonceux Castle, which is where the Royal Observatory was, so perhaps it's not so different. Anyway, there he was. Now, I want to come to Johann Kepler. He was 6 when he saw the great comet of 1577, got interested in astronomy. He saw the lunar eclipse of 1580, a total eclipse of the moon. There is an eclipse on the 21st of December, but it's as dawn comes, and full eclipse isn't until the moon's actually below the horizon, but you will see part of it. But if you come with me to the Caribbean at that time, we'll see it nicely in the sky. Okay, so he became and he had his own ideas about the orbits of the planets. He knew that Tycho had this wonderful database, so he went to Tycho and said, "Can I come and join you and use your data?" Tycho was a bit wary of him and really didn't want him to do too much, but he let him come anyway. So that's what was going on. But then fate intervened. Tycho died in 1601. He'd been to a banquet and was too polite to go to the loo, and it is said that that might have been a bladder infection. However, they did actually look at his body, and I think it was 1991, and they found in his hair the evidence of rather a lot of mercury. So the thought arose that he might possibly have been poisoned. And I think that's just showing you the various elements in his hair. The great thing about hair is, as it grows, you can measure how far it is from the root. You know roughly when whatever it was administered. So he may have been murdered. There are two suspects. One is Kepler himself, who it is said had the means, motive and opportunity. He could easily have put some mercury in with milk. They think they found some calcium as well, so it might have been in milk that he had. He might possibly have dosed himself, but we're not sure about that. But the other the other possibility is he was murdered by a cousin who was called Count Erich Brahe, who actually came to Tycho's castle just a few days before the banquet. And it is thought that might have been on the orders of the son of the first king, King Christian the Fourth of Denmark, who thought that Tycho was having an affair with his mother. So these are the two possibilities, and so people would like to know whether he really was poisoned or not. And the reason I've told you all about this is that Monday a week and a half ago, anyone see in the news? They've actually exhumed Tycho's body. This is the little casket, a tin casket he's in, that says Tycho Brahe. And that's a recent picture of about 3 or 4 days ago, looking at the various bits. He seems awfully pleased with himself, doesn't he? But I don't know what that bit is. But the hope is by analysing his various bits, and particularly the hair, they might be able to be sure or not whether he really was murdered. So that's why I thought I'd tell you that little story. Right. And, oh, we've done a few minutes into the right time, but you should all be here by now. So, voyages to the outer solar system. There's a problem with talking out about the planets. There are so many facts, and I don't like remembering facts. I think that's a waste of one's brain. I know they say that people that know all these things in these quizzes are very brilliant, but I'm not convinced that's true. So I can sometimes work things out. What's the diameter of Jupiter, as a matter of interest? I don't know, not as a number particularly. I know it's about 11 and a bit times the size of the Earth. How big's the Earth? One thing I do know is that to go once round the Earth, it's 25,000 miles, and that's because that's how far they have to sail when they sail around the Earth. And I always think that's a cheat, because they don't go through the Panama Canal and the Suez Canal and go all the way round, do they? They go all the way down, they just skirt round Antarctica and come back up again. As far as I can see from the rules, if there was a buoy on the south, at the South Pole and no Antarctica, all they have to do is go down to the buoy, turn around and come back. And I do agree that that's actually a dangerous thing to do, probably more so than going around the middle. But nevertheless, that's 25,000 miles. Divide that by pi, it's about 8,000 miles diameter, times 11, you're about 88,000 miles diameter for Jupiter. So you can always work these things out. And what's Wikipedia for? And look, I know we laugh, but in fact, in terms of the scientific things in there, it is pretty good. And in fact, even I keep some pages of Wikipedia for the square kilometre array. So I have to say they're good, but you can find anything you want. So why should I try and tell you lots of facts and figures? I want to tell you the things that I have found interesting over the last 30, nearly 40 years as spacecraft have gone out through the solar system. So it's using my memory, or lack of it, as a filter to say what things are interesting. Because if I think they're interesting, I hope that you will as well. So the first two spacecraft to go out beyond the inner planets, that's beyond Mars, were Pioneers 10 and 11. They left the solar system having visited Jupiter and Saturn. I won't show you many pictures, I just want to show you one thing. These things are going so far out, they can't possibly get their power from solar panels, so they have what are called radioisotope thermoelectric generators. What means is that in here they have something like plutonium, which decays, produces heat, which then is converted into electricity. And in fact, when Galileo was due to leave some years ago, there was actually a court case because people said, this is dangerous. If this actually crashed after takeoff, it could actually pollute the Earth. And there's something true in that, I suppose. Anyway, so they all have these RTGs, as they're called, and they have to have pretty big antennas to send the data back to Earth, and all sorts of instruments, of course. Now, there was a real problem, or still is really. They weren't totally sure that the Pioneers would get to Jupiter, because on the way, you've got to go through the asteroid belt, and I'm about there, I think that's me. No, I have a little one. It's only 5 kilometres across, named after me, so it's there somewhere. Anyway, and they didn't really know how dense the material was. We know of the big ones, but we didn't know how many small ones, or little bits of dirt and dust. And if you're travelling at 50,000 miles an hour, or that order, even a grain of dust can totally destroy you. Well, happily, it looks as though there aren't too many very small particles in the asteroid belt, because all of the spacecraft that have gone through to date have got through safely, so that's good. Anyway, they got to Jupiter. I have to say that their cameras weren't all that brilliant. You don't find many really good pictures. In fact, to be honest, you can get better pictures from the ground now, from Earth, than the Pioneers took. But there you can just see the great red spot and these bands, the equatorial bands of Jupiter. That's a slightly better one. This is Pioneer 11, and that one, for the very first time actually, did photograph the south polar region. That's something you cannot see from Earth, so at least not very well. So that, I suppose, was a beginning. Now, Pioneer 11 was then sent on to Saturn, and it got there in 1979. In fact, what's a near miss? It got within 2,000 miles of a newly discovered little satellite called Epimetheus. That's what its picture of it was as it was on its way past. That's a much more modern picture. But anyway, that wasn't known about, so there's always a chance these things will hit something on the way. It didn't, happily. It took these pictures of Saturn and Titan. There you can see Titan. You don't see any details visually because it's shrouded in methane clouds, so you don't see the surface at all. And to be honest again, the images of the rings weren't all that brilliant. But nevertheless, what they did find out was that there's a very high level of radiation around these planets. And that meant that they could harden the electronics of the later satellites so that they could survive perhaps when they were in orbit about Jupiter or Saturn, and hence being radiated for a long time. Now, two things that the pioneers did that aren't to do with the planets, but were nevertheless quite interesting. I was involved, and you've probably heard this a few years ago, with what was called Project Phoenix, the final phases, when we linked the giant radio telescope Arecibo, the world's biggest, with the telescope at Jodrell Bank, to simultaneously observe about 820 sun-like star systems in the hope that ET might be phoning home. And if you remember, you might have seen Arecibo in the Bond film GoldenEye. I doubt whether you look at Bond films. Anyway, I think Pierce Brosnan and the baddie had a fight up here, and the baddie fell down. I'm told that Pierce Brosnan never went anywhere near that. They said it was far too dangerous. I went up there a few years ago, and you walk up here, which gets quite steep, actually, and they suggest you have some spare bits and pieces with you in case. Anyway, it was quite exciting. So that's Arecibo, and that was linked with Jodrell Bank. Now, the important thing is this. Because they're on opposite sides of the Atlantic, any local interference picked up at Arecibo will not be picked up by Jodrell, and vice versa. Is that fairly obvious? But also, as the Earth is going round, in fact, we have to receive signals at slightly different frequencies, which means that we're not sensitive to either local interference or even satellites in orbit around the Earth or even around the Sun. Together, we will only detect signals that are coming from beyond the solar system. That, of course, made the 5 years or so that we did it, 6 years, a bit boring because we never had any false alarms. But if you have such a sophisticated system, and it really was the most sensitive and sophisticated system that's ever been used to search for ET, how on earth do you know it's working? Well, every day, at least twice a day, we were able to pick up the Pioneer 10 signal. It was radiating with initial power of about 3 watts, and we could observe that at least once a day, and it was about 10 times above our minimum detection limit, and that, in fact, is the signal from Pioneer on one of our observations. So we knew the system would work. Sadly, it died just about the last set of our observations in January 2003. So that was a very useful feature of Pioneer 10. Now, I hope we've got no kiddies here. We're all right. It was the first, these two were the very first craft to leave our solar system. And Carl Sagan, who you may well have heard of, he thought it would be a nice idea to put on them a little plaque, so if anybody ever found them in the far future, they would learn something about us and where it had come from. So down the bottom here, you see the Sun and the planets. It shows that the spacecraft came from the third rock from the Sun. The Earth came past these bigger ones and out. That's good. This, by the way, is hydrogen. It shows you the proton and the electron. And the proton and the electron can either have their spins in antiparallel or parallel. If you get a transition from one to the other, out comes a photon with a wavelength of 21 centimeters. We know that. Any other advanced civilization would know that too, and we know that they know that, and vice versa. Anyway, so the point is, we give them, with that diagram, a measurement of length. And that's used here, by the way, to measure the height of the young lady. Although, of course, you've also got the spacecraft size as well. Perhaps the most interesting thing here is this little picture. If we were, as I have done, sailed across to the Channel Isles, you could actually see quite a number of lighthouses. Now, in the days before GPS, you could work out where you are from the various bearings to the different lighthouses. You'd know which was which because of their flash rates. Fair enough? Well, here, in fact, from the Earth, or from the Sun really, are the directions in the galactic plane of 14 pulsars. We've talked about those in the past, along with their flash rates. So anybody who picked that up could actually work out where our Sun was, and because the flash rates, the pulse rates of pulsars slow with time, they might even work out when it had left the Earth. That's all rather clever. So those plaques are on their way out to space. There was a minimal bit of censoring by NASA before it was sent, but nevertheless, NASA did get some opprobrium from the American Ladies League of Decency and various others for sending naughty pictures into space. And that has a result that you'll see later on. Now, I have to tell you, sadly, that it ain't going to last all that long, because in 2287, I'm told, under good authority, it will be used for target practice by a Klingon bird of prey. So anyway, we'll see how long it lasts. Right, so those are the pioneer missions, and they led the way to the more sophisticated Voyagers. They both went past Jupiter. Their cameras were a good bit better, and they didn't actually make all that many images of Jupiter itself, but there you see the equatorial bands and the red spot here, along with some of the little satellites. We'll come to those shortly. A nice picture there of the great red spot, and an even more detailed one. That's a mosaic which was produced in 1979, in March. This is a giant anticyclone. It's going around in an anti-clockwise direction like that. It is not fixed to anything because it's floating in the atmosphere of Jupiter. It stays in the same latitude, -22 south, or -22, I should say, but it actually goes round. Over the time it's been seen, it does actually move a bit around the Jovian sort of interior as it stands. But it's big enough, in fact, to be essentially stable, so it's remaining, we don't know for how long. Certainly seen since 1831. Now, Galileo observed Jupiter's 4 major moons with a little telescope. Those are some pictures he drew, or had drawn for his book. Incidentally, someone called Simon Maris claimed to have discovered them at the same time and gave them names which actually are the names that we give to them now. Io, Europa, Callisto and Ganymede, the 4 Galilean moons as we call them. And there you just see them, Io up top, Europa, Ganymede and Callisto. Io, even with an 8-inch or 10-inch telescope like I have at home, does look a little bit orangey, and it really is. And this is a mosaic that Voyager made, and you see it's pot-marked with what look like craters and volcanoes. And in fact, they found a total of 9 active volcanoes between them as they actually went past Jupiter, and evidence of some other ones in between the first flyby and the second. And there you see one of the images that shows an active volcano. We'll see some more later on, but that was really perhaps the most exciting discovery. Io is 10 times more volcanically active than the Earth. Not a nice place to be. The white there is sulfur dioxide ice, and there's lots of hydrogen sulfide gas around as well, and the colour comes from lots of sulfur compounds. Something that's been discovered fairly recently, it's fairly obvious I think, this is not a real image. People have tried to work out whether Io is in thermal equilibrium. You can get an idea, where's the energy come from? It's tidal forces from Jupiter. You know the moon makes the tides go up and down on the Earth. That can actually make little stones rub against each other, a little bit of heat by friction. Well, the surface of Io is going in and out by about 40 meters. It's a bit like an accordion. And that causes an enormous amount of friction, and that generates heat, which is why it is molten. Now, they've recently made infrared studies to measure the amount of heat radiated away from Io, and it all works out rather well. It looks as though it will remain in this sort of state for a very long time to come. The Voyagers then went from Jupiter off to Saturn. In fact, I should lie, one of them did. They went to Saturn, and that's just a picture of them above the rings of Saturn. They discovered that there's a thing called the F ring. It's here, an outer ring. That's braided, and we'll see some more pictures later on. So that's a new ring. It was actually first picked up, I think, by one of the pioneers, but not at all well. But that at least shows you it there. We'll talk about what the rings have to show us a bit later on. And there's Tethys and Dione, and you see the shadow of the rings on the surface. And Rio and Dione down the bottom here, some of Saturn's satellites. That's called the Cassini division, and that's called Encke's division. That's quite easy to see with a relatively small telescope. Encke's division is a good bit harder. The seeing conditions have to be very good indeed. It does have bands like this, a bit like Jupiter, but they're not nearly so prominent. Rio, mostly made up of water ice. That's the surface of Rio, close-up picture. And Mimas, this is rather fun. Mimas has this big crater. And apparently, if that crater were much bigger, Mimas wouldn't be there, it would have broken up. So it's about the largest size crater that an object that size, or impact, it could actually support without breaking up. Mimas has another interesting effect. It causes Cassini's division. The gap between those two major bands is basically because that's a resonance with the orbit of Mimas, and any little particles in there tend to get gravitationally shifted one way or the other. So all these little ringlets you get in Saturn are all basically the result of the satellites in orbit around it. And the biggest one, the Cassini division, is the result of Mimas. Enceladus, we're going to come back to later on, a very, very interesting satellite. It's very bright, ice-covered, as we shall see later. And even though it's quite small, you can actually see it with a relatively small telescope. Iapetus. I mention this one because it's very interesting. Cassini, he named Cassini's division, or it's named after him. When he observed Iapetus, he could only see it on one half of its orbit. It was there, obviously, some of the time, and it wasn't there the other part of the time. And it turns out it's got two faces. One face is very bright, this one. That's the trailing face, though it's ice-covered. But the leading face is covered, we think, with carbon-type compounds, and is actually very dark, which is why he couldn't see it. When it was actually coming towards him, he couldn't see it. When it was going away, he could see the back side, which is very bright. And that's a rather nice mosaic of Saturn with its moons, all taken by the Voyager craft. And up here, of course, is the satellite Titan. We're going to say more about this when I talk about the Cassini spacecraft towards the end. So, Voyager 2 left Saturn to go to Uranus and Neptune. Voyager 1, they got to have a closer look at Titan. More of that later. But Voyager 2 carried on and went to Uranus and Neptune, the only spacecraft so far that have been able to do that. And the reason they could do that was because of not a chance alignment, but a rare alignment of all of the outer planets, all basically on one side of the Sun. Do you remember people getting very worried about that? You know, the whole thing's going to fall apart. Just because you could see them in a line and they're all outside on one side. The whole solar system was going to fall down like that. Ridiculous. Anyway, the point was, it was worked out that once every 175 years that happens, it would be possible to get a spacecraft to work its way all the way out. And the idea that lets you do that is by basically using close flybys of satellites to gain energy. They're called gravity assist flybys, or sometimes gravity slingshots. Now look, if this was a racket and here is a ball or something, if I did that, can you see I can give energy from my racket to the ball? Obvious. And it flies off at a much higher speed. We could get anyone, a good tennis player, to come and demonstrate. Right. However, supposing this is Jupiter going along like that, or I'll make it do it this way, and I bring a little spacecraft just round the back. Can you see that's gravitationally attracted to Jupiter? And if that was stationary, it would fall in. But it's not. It's going very fast. So what happens is it picks up a lot of speed from Jupiter and flies off in that direction. Do you get the idea? It's almost as though here it was, and here's Jupiter that gives it a hit. The same basic idea. So you can gain, essentially, Jupiter's orbital speed around the Sun. And that gives it a jolly good boost to get out towards, in this case, Uranus and Neptune. In fact, Voyager 1, because it went past Titan, just went out through the outer solar system as well. I'm sure you know that Uranus was discovered serendipitously by William Herschel. He'd made a superb telescope. The optics were far better than any telescopes that had ever been made to that date. And he'd seen something that looked, first of all, like a comet. But he realized it wasn't a comet because it didn't move in the way that comets moved. It was barely moving through the sky at all. And it didn't take very long to find out that it was, in fact, the first major planet to be discovered in modern times. And he obviously became very famous and astronomer royal, all that sort of thing. Wonderful guy. More recently, it was discovered to have some rings. It's an interesting story, that. every so often, planets will go in front of stars, a planetary occultation. If you observe a star coming behind a planet, can you see the light from the star will briefly go through the atmosphere when it goes in, and it will go through the atmosphere when it comes out. This enables you, if you analyze the light from a distant star, to learn about the atmosphere. Does that sound plausible? So people do that, and it's a difficult thing to do from the ground, so this was being done by a telescope mounted on a high-flying aircraft. They set up observing Uranus a good 40 minutes before the occultation was meant to happen. About half an hour before it, the signal suddenly disappeared, the signal from the star. And they probably said, "Oh bother," or words to that effect, because it looked as though their system had just stopped working. About 5 minutes later, the signal reappeared. For no apparent reason, they all gave a sigh of relief. But then a bit later, it disappeared again and again and again and again. Not so much. It just dropped down and came back up. And they twigged that the light from the star must be being hindered or occulted by a ring system. So when it came out the other side, they did the real experiment, they kept on observing. They didn't just pack up. And the same thing happened in reverse. Can you see? As the star would go across here, it would be occulted by this first major ring here, then these 5 minor ones. There was 1, 2, 3, 4, which they picked up as well. There are 5 in all. And then can you see you get them in the other direction, on the other sequence. So that's how those rings were discovered. They are exceedingly difficult to see from Earth. The Hubble Space Telescope can just about show them, but not really to any extent. And that actually is a picture of them taken by Voyager 2. It shows the outer thick ring and 1, 2, 3, 4, 5, 6 in 3, 4, 5. And there's a few there as well, actually, but 1, 2, 3, 4, 5, 6 major rings. And the thing that can actually keep these rings in place are if you have some moons. And it's rather lovely. Here's one moon, here's another. And these are the shepherd moons that actually marshal all that little bit of debris that's actually going around Uranus. And that's about the best image we have of the ring system of Uranus taken by Voyager, when it was basically, well, rather beyond, away from the Sun. You see the rings quite well, actually, when the Sun is on the far side. Just as a matter of interest, Uranus has got some moons. They've got nice names: Ariel, Umbriel, Titania, Oberon, Miranda, and Puck. That's Puck, the little baby one there, which all come from Midsummer Night's Dream, I hope. And they're not easy to see, but they are there, certainly. And they're rather nice little moons. Nothing particularly exciting about them, to be frank. Except when Miranda's interesting. Here's Miranda, and there's... Notice Uranus, it's a lovely sort of turquoisey colour, but it has absolutely no features at all. It is totally featureless. And you can quite easily see it with a 5-inch telescope. It's not, in fact, but binoculars will pick it up. And earlier this year, it was very, very close to Jupiter. So you could find Jupiter, and then just with binoculars, you'd see it in the same field of view. Sadly, they've moved apart in the sky now. This is Miranda. Miranda's really rather fun. When kids have plasticine, it comes in these nice little strips of different colours, isn't it? And it doesn't take long before they muck it all up. You know what I mean? And it goes a dirty brown colour. Well, this is sort of part way through. It's as though several little bits have all been stuck together. And it's thought that Miranda may have been hit by something, broken up, and then those bits, by gravity, come back and sort of vaguely fit together in not a very good way. It has become pretty well circular. It's big enough to do that. But can you just see all these different bits of terrain? It's really quite amazing. And there's one very interesting feature, which is down here. And let's look at that in close-up. It's called Verona Rupis. It's a cliff, and it's somewhere between 5 and 9 kilometers high. And quite a nice little exercise to give your students is to ask them, if you fell off the top, how long would it be before you hit the bottom? Any guesses, by the way? Anyone like to guess? Sorry?
Instant almost?
A bit longer than instant. Not 3.5 minutes. Not bad. Well, look, it depends on how high it is. But I did this calculation. You can work out that the surface gravity on Miranda is 130 times less than on the Earth. And that means it's going to take, you know, you're not going to be accelerated so quickly. A height, 5 kilometers, it may be a bit more than that. If you do the sums, you'll be falling for over 6 minutes. So you have a nice long time to think about your past life and all that sort of thing. So anyway, that's Miranda, which is really rather fun. And here is a lovely view just showing the rim-lit Uranus as Voyager left for the planet Neptune. Again, I expect you all know the story of the discovery of Neptune. This is the orbit of Uranus, and that is Neptune. And you all know that the planets nearer the Sun go round more quickly, so you can appreciate that Uranus would have been travelling around sort of on the inside track, all right? So it would do something like this. In fact, you can do this in a frame of reference where, in fact, you make Neptune stationary, and then this just goes around a bit of a different speed. But look, just supposing Neptune was here and stationary, all the time it is ahead of Uranus, and there's a bit of gravitational pull that way. Can you see there's a component that's trying to make Uranus go faster? Any force that way has a component at right angles to the Sun and one at that way. So essentially, you get a bit of a pull, making Uranus go a bit faster than it would otherwise do. So it will get ahead of itself. It won't be in the right place. But notice, once it's gone beyond Neptune like this, can you see the forces in the opposite direction? So it slows down again. Now, what they'd observed was that Uranus was doing that sort of thing. It was getting ahead of itself, then it stopped getting ahead of itself and sort of went back to where it should have been. And it was deduced that there would be a planet whose gravity was making that happen beyond Uranus. And two people, John Couch Adams at Cambridge and Urbain Le Verrier at the Observatoire de Paris, both decided that they could calculate where it was. Adams made his calculations. He took it to the Astronomer Royal, who was having dinner and didn't see him. He left a little letter behind. The Astronomer Royal Airy couldn't understand Adams' calculations, and I don't blame him for that, because people who've looked at them more recently can't understand them either. Anyway, the point was that Adams produced a position where this planet beyond Uranus should be, as did Urbain Le Verrier. The trouble with Le Verrier was that nobody liked him. He was a bit of a pain in the proverbial, and no one took any notice. He actually wrote a letter to the British Astronomer Royal as well, Airy, and said, look, I've got this position. The two agreed quite well, more by luck than judgment, actually. So Airy thought he ought to do something about it, and he got the Chadwick at Cambridge to use a telescope there to try and discover the planet Neptune. The trouble was that we didn't have a good chart of that part of the sky, so he had to make one. And of course, you don't get all that good weather in Cambridge for observing every night, for example, and occasionally you might have something like a college dinner, which takes precedence, of course. So he wasn't doing it very, very quickly. On one night, it is said, he actually spotted something that didn't look quite star-like. But that was too late, because Le Verrier let some friends at Galileo d'Arrest at the Berlin Observatory know his position. Now, there was a bit of European cooperation going on. A big new star atlas was being made, but rather than every observatory do every bit of the sky, different observatories were doing different parts. And the Berlin Observatory had just done the bit where Neptune should be. But because the post wasn't quite as good in those days, and we didn't have the internet, that star chart had not left Berlin. So all they had to do was to look at that bit of the sky, tick off all the stars they knew about, and find the missing object, which was Neptune. So, in a sense, the discovery went three ways: Berlin for the actual discovery, Le Verrier and Adams, who basically said where it would be. So that was how it was discovered, a rather lovely planet. This is Voyager 2 going to Neptune. It's a much darker blue, and it's got some features, as you'll see. It's got the great black spot, or this region here, dark blue spot. There are clouds, as we'll see in a minute. That's called the scooter, and that's called the eye, for reasons that will become apparent. Now, rather like Jupiter and the Sun, the different parts of the surface rotate round at different speeds. And they worked out that there would be a time when all of these three would be sort of roughly lined up. So then they could take that picture there. So here is the eye, that's the scooter, and that's the sort of the great dark spot here. So it has got some nice sort of details on the surface, and these are very high altitude methane clouds. Neptune has a moon. It's called Triton, and here is looking back towards the sun as Voyager was leaving Neptune, and here you see a little bit of Triton as well. There are very few craters on the surface. That's a close-up picture it took. Remember, this is the only spacecraft that's ever been there. And really, on that image, you just see one crater, maybe one or two more down here. That implies it's geologically active. The surface isn't old. Otherwise, there'd be a lot more craters. And there's one part of it that they call cantaloupe country. And I'm not really into it, but isn't there a cantaloupe melon, which looks a bit like that on the surface? So I'm told. Anyway, I should go to my local greengrocers and find out. So that's two close-up pictures. But perhaps this is the most interesting picture. This is the South Polar Cap, and it's solid nitrogen, but there are geysers. Look, here, here, here. There. Little streaks. This is stuff coming out. And it looks as though nitrogen below the surface is becoming sufficiently warm to vaporize and come out in little jets like that, putting dirt over the surface, bringing up some probably carbon compounds. So it isn't in fact totally dead, even that far away from our sun. They discovered two small satellites whose names I don't know, and if I told you, you'd forget within a minute anyway, so there's no real point. Neptune has got some rings as well, and that's one picture showing them. They're not very prominent. And again, this is a picture taken as Voyager had left Neptune on its way out into the outer solar system, and you can see those are the two main bands, but there are also some hints of some broader, fainter ones. Where do these rings come from? Probably they're little bits of dust which come off some of the satellites when they get impacted by meteors. So you get an impact, a little bit of dust is thrown up, and they can form these little rings. So you see, Jupiter, as we'll see, and later I think, and Saturn obviously, but Uranus and Neptune have all got ring systems. Okay, well again, these two craft were going to leave our solar system, and they got slightly more ambitious. Let us put really an early version of a CD-ROM. CD-ROMs you get with pictures and all sorts of videos and sounds, whatever. They made one, and it was a gold-plated disc like this. There were some instructions on the cover. This is the cover to tell you how to play it, and they included a stylus, so you could do that. Even tell you how to do it. Down here, by the way, the same measurement system. That's the hydrogen atom. Do you remember the pulsar directions? That's all the same. This is basically details of playing the record. So on the record, they had lots of things. It actually calls it the sounds of Earth. And one interesting thing is they actually put on the surface a little bit of uranium, pure uranium-237 or 8, I think. And the point is that decays with a half-life of 4.3 billion years. So if this was ever found, and they looked at the uranium and the daughter products, can you see they could work out how long it had been sailing through space? So that was a bit of fun. So anyway, there were lots of pictures and sounds and things. Let me give you some idea. These are just a few of the images on it. The one on the left there is to tell you about number systems, and they're using binary code. You can see down here, this is binary and our numbers that we use, so binary and decimal. That's all rather fun. This is all about the DNA and the genetic code, which is interesting as well. A picture showing the idea of continental drift. You can see what's happened in various times in the past. I mentioned they had some trouble, so all of these were discrete silhouettes. There was one previous picture in this series, but you can't find that on the web for some reason. Anyway, it's the one that goes before the little baby, so it's fairly obvious what it's about. But they're all very discrete silhouettes, and that's our little fetus there on the right. Picture of the Arecibo telescope, 305 meters across, that we've mentioned earlier. A lot of sounds. What the music of the spheres was meant to be about, I have no idea. but sounds of crickets and frogs and dogs, and a Saturn V liftoff, that would be rather good. A pulsar, that's fairly obvious, Morse code, all these nice things, they're all there. Then there were greetings from children and adults in all sorts of languages. I think Sumerian, that may be the oldest active language that we know of, I think. And I think the final one was English kids saying greetings from the children of Earth. I think that was in English. So that gives you an idea of that. There was also a lot of music. I've only just picked up 4 of them here. Some of them obviously were more modern things by Bach and Beethoven and even much more modern composers than that. But they also had Pygmy Girls, initiation songs and panpipes from the Solomon Islands. Lovely things, just to give people a feeling of what the Earth was like. Now, the probability of anyone ever coming across that in the future is essentially 0, but I think it's a rather nice thought. A nice picture of Newton's book, and you should have seen this if you've come in the past, you might have seen this. This is where Newton, in not a book for the general public rather than for scientists, is basically making the point, if you fire a cannon from the top of a tall mountain, obviously it will fall to the ground. It's above the Earth's atmosphere, so there's no friction, no air resistance. The faster you fire it, the further it goes. And if you fire it fast enough, which is about 18,000 miles an hour, it will go all the way around and hit you in the back of the head. And this was to try and make the point that the moon is falling as well. It just happens to be falling at the same rate that the curvature of the Earth makes the Earth fall away, and so it remains in orbit. So that was a nice picture, I think, of that. And there's some music here. It said it was cavatina, but I read music. I can't see cavatina in that. Anyway, it doesn't matter. There's a nice violin and some music. Whether they could interpret that, I don't know, but they could have a go. So, that was rather nice. So, we're now going to have a look at the final 2 major satellites, and then briefly one that's on the way. Galileo went to Jupiter. It was launched in 1989, and it arrived a long time later in 1995. It took a very long route to get there, and that's because it was a very big, heavy satellite, and they didn't want to spend too much money trying to build a very big rocket. Did you notice that the world's biggest rocket to date launched something 2 days ago? Something matter. It's a spy satellite, and it used an enormous rocket to put it up there, but they didn't use that for this, they used a relatively small one. So, in order to get to Jupiter, it had to go a very long way round. Now, it was launched here, the Earth was here. It first of all came past Venus, and it did a gravitational flyby, a slingshot there. It came back round to the Earth, did another slingshot here, so it's picking up speed from, first of all, Venus and then the Earth. Then it goes all the way around and it comes back to the Earth, but on the way, it went past the asteroid Gaspra in October 91. Leaving the Earth after its second flyby of the Earth, so that's 3 flybys, it passed the asteroid Ida in 93, and then finally got to Jupiter in 1995. And on the way, it took a very nice picture of the asteroid Gaspra, and then later Ida, and for the first time, a little moon of an asteroid was discovered. That's called Dactyl. Quite why, I don't know. One nice thing, in 1995, actually let's say 1994, a comet had been captured previously by Jupiter, got so close it broke up around the back, and the little chunks, about 24 of them, all started orbiting in a very long ellipse Jupiter. And they were discovered by some lovely people, the Schumachers and Levy, David Levy. Shoemaker-Levy 9 was the name of the comet. And basically it was a train of little comets. And they were all going to impact Jupiter the following July, just before, a little bit before, Galileo was going to get there. Now the trouble was that the impacts, as seen from Earth, were round the back of Jupiter. We couldn't see the impact sites, but Galileo could. And that's just a sequence of 4 images showing the impact of the W bit, because they had the letters A to Z, basically. There were about 24, 25 of them. This is the only pictures we actually have of the actual impacts. There are pictures of the plumes that were sent up shortly afterwards, taken by the Hubble Space Telescope. And then, even with our small telescopes on Earth, we could see these giant basically regions of dirt covering up areas about the size of the Earth on Jupiter. So that was rather nice. And that's a more close-up picture showing you one of the moons there. Again, you can see the moons and their transit from Earth. This is a better picture you can take from Earth, but it's surprising what you can do now with the current image processing techniques we have. And the close-up there, the red spot, really nothing better than they got with Voyager in terms of looking at the surface. It spent much more of its time, or has done, looking at the satellites. But a nice one of the swirls and the eddies around the great red spot. There's Io again, and you can see it's orange looking. And here are some photographs, and you can see that over time the surface changes. That's an earlier picture, that's a later one. This here has obviously erupted and caused this region around here to be covered with this dirty thing here. So it is a surface, as we've said, which is active in terms of its volcanism. And this is a nice picture, some real lava coming out here. I've only seen that once on Big Island, Hawaii, where you can actually walk down to where the lava's coming out of the ground, and that's quite an exciting thing to do. So there we go. That's a real picture of the volcanoes on Io. But perhaps the most interesting thing comes with Europa. Now, in complete contrast, it has this lovely icy crust. There are cracks on it, as you can see. That's caused by the tidal flexing, the tidal forces of Jupiter. When they saw those pictures, they thought these cracks would be very deep, gorges, if you like, but they're not. It's like someone's just put felt-tip pens on the top of a piece of paper. They're incredibly shallow cracks. And the idea arose that essentially we're looking at a surface of ice that is overlaying an ocean of liquid water. And you can see icebergs. Let's just have a little bit of, not ice, but the result of ice. If you look over here, can you see, it's pretty obvious there and perhaps there, that the surface is cracking. You see it breaking apart. It looks as though the surface, cracked by the tidal forces, breaks apart, and then immediately water wells up from underneath and freezes. So the surface is dynamic and floating, as in this diagram here, on a fairly substantial ocean of liquid water. There's a lot of water here. It's actually quite a thin layer if you look at the overall size, but nevertheless quite significant. So we have this region of liquid water, probably a bit salty. But of course, if you've got water, it is not impossible that somehow life could arise. And as we believe that life arose on planet Earth around these hot underwater thermal vents near the oceans, in the center of the oceans, it may be there could be some tidal force-induced heating that could give rise to thermal vents there. Maybe sometime in the future, probably not in our lifetimes, I'm afraid, a spacecraft might go, a little probe will go around and have a look to see if it can find any evidence of life. And that's significant for something I'm going to say very shortly. Nice picture there of Ganymede, and there's one of Callisto. Now, they were very keen that Europa should never ever be contaminated, just in case we took things from Earth to it. So, when the RTG on Galileo got to the point that it could no longer give enough power, they arranged for it to actually dive into the Galilean atmosphere, Jovian atmosphere I should have said, at a speed of 50 kilometers per hour, and essentially this would burn it up, so there was no chance of any contamination of Europa. Well, the final main mission I'm going to talk about is Cassini-Huygens, and that is perhaps a wonderful mission which is still ongoing. Galileo drew this picture of Saturn. He didn't really understand it because it had these ears, like that. This is a simulation using a telescope of about the size that Galileo had of what you would see. And you obviously cannot make out the ring system. He got even more confused when they disappeared. And then they came back again. And the reason, of course, is that we see different aspects of the rings at different times, and occasionally the rings get very close to edge on, as they were last year. And in fact, that's some pictures taken by the Hubble Space Telescope at about the time when the rings are edge on to the Earth. And the whole idea is simply this, that the rings, the rotation axis of Saturn is inclined to the plane of the ecliptic, and so here we're looking at the underside of the rings. At that point, we see them much narrower. Here, they're essentially edge on to us, we see that. And then they open out again, and this time we're seeing the top as opposed to the bottom. So you get this sequence, we get two edge views each orbit. Cassini went very close to the rings, it then went into what's called the orbital insertion, started orbiting Saturn in quite a long elliptical orbit, so it could go out and look at all the satellites as well. And that's a wonderful view of the rings that's taken. So you see they're not continuous bands, they're lots and lots of ringlets, little particles going around. They range in size from perhaps a millimetre or less up to a few metres across. 90 to 99% of them is water ice. I was reading something, in fact, on the train yesterday coming down from a meeting at Gresham, that in fact the lady who's responsible for the Saturn rings observations of Cassini says that we'd love to know what they're really like. We don't know if there's like fluffy snow around the solid core or just like more dense snowballs. We don't know. These are the names of them. I've already mentioned some of the points. The A ring is the outer one, the main outer one. It's got Encke's division in here. This is Cassini's division, kept there by Mimas, of course, as I said. The bright ring, or the B ring, and then the C or crepe ring is a much fainter one inside. And that's just another view showing that rather nice F ring, which is orbiting further out. Quite a dramatic view there, isn't it? Showing you the F ring up at the top. A ring. That's actually seen almost in inverse because the bright ring is actually looking dark. And these are rather nice pictures. That's actually showing Titan here. But you see the sun is causing, or the rings are causing shadows on the surface. And so you sort of get a negative of what the rings look like. And you can just make out this F ring just out there. The Cassini division, the Encke division. And that's just the same thing but shown much larger. And the F ring here, Encke's division, Cassini's division. I think that's right. Actually, I think that might be the Encke division. This is another one which has a name, but I don't know it. And that's just to show you what it might look like if you got there. These conglomerations, clumps of these little particles, up to a few meters across. The whole thickness of the rings is only a few kilometers. It's really a very narrow thing. No one's quite sure where they came from. Because there's so much water ice there, I think most people think they actually were formed about the time of the formation of Saturn, that they're very old. Because if you broke up something now, there'd be a lot more carbon compounds around, and they are very bright and essentially all water ice. So that's still an unsolved problem. There's some spokes, you see, which are rather interesting. They've been seen from the ground by a wonderful observer called David Livy, Shoemaker Levy 9, same chap. He'd seen them when he was a young guy, and he wondered what they were, and people said, no, they can't possibly exist. You're lying. Well, he wasn't. There they are. The F ring, that has a little satellite called Prometheus very close to it, and you can see it causes some nice little kinks in the rings like that. There's Prometheus there. Looks very pretty. This is done when Saturn was edge on to the Sun. The rings are just lit up by the reflected light from Saturn itself, so they're barely visible. It looks a lot better, actually, on the computer screen. It's not really quite dark enough, but it's actually showing the rings by reflected light. The Sun is right in the plane, which happened last year. So that's a very recent picture. And just to finish with Saturn, at least the rings, isn't that a wonderful picture? It's one taken when Cassini was essentially right behind. The Sun was basically behind Saturn. So you're just seeing all the rings lit up like that. That's absolutely beautiful. Cassini. That's actually helped Einstein and general relativity. Essentially, there's a thing called the Shapiro delay. It was discovered in 1964 at a place called the Haystack Antenna in America. You know when you're getting old, when your friends become directors of observatories. You know you're getting very old when your research student becomes the director of an observatory. And my research student, Colin Lonsdale, was made director of Haystack last year, which I'm very proud of. I can't have been too bad for him. Anyway, the point is this. They send signals by radar from here, let's say to Mars and back. And if they go past the Sun, something happens. Imagine here's the Earth. You send a radar signal to Mars, and the Sun isn't there. It goes straight there and back, straight line. If the Sun is there, because it distorts the space around it, that basic path of that track, can you see it's going to curve? That's what happens. So it would miss Mars. To get a signal to Mars and back, it's got to go on a longer path. Is that at least plausible? I promise you it's true. And that means it takes longer. It's called the Shapiro delay. And it's up to basically a couple of hundred microseconds. This is just a simulation. Look at the number up there. When you're very close to the Sun, it's about 190 odd microseconds. That's been done with Mars, but also with the Voyagers at Jupiter. But it was done with Cassini not that long ago. They send signals to Cassini, it then immediately responds back like an identification oh dear, you know, IFO, friend or foe, identification friend or foe. And that means you can measure the time to there and back very, very accurately. By using two frequencies, they could eliminate the effects of the corona of the Sun. And they basically got a delay which agrees with Einstein's predictions to 1 part in 10 to the 5th. And that's probably one of the very best two tests of Einstein's theories that's ever been made. So well done, Cassini, for that. Saturn has some moons, and that's a little picture I took. When you're going into Google looking for images, it's fun when you find your own. And that's one I put on the web a long time ago. And it just shows with a baby telescope, Saturn, and that's Titan. And you can see 1, 2, 3, 4, and actually 5 moons. They're the 5 brightest ones. And that Iapetus, Rhea, Iapetus, Rhea, Dione, Tethys, and Enceladus, which is quite small but very bright. So those are the main moons. And there's Rhea and Janus. And this is rather fun. Look at the lower right one. This is an occultation of Dione by Rhea. So there have been some lovely pictures taken by Cassini of the satellites. Iapetus, it shows you this very bright white side and this very dark backside, and this rather nice ridge around the middle. It's quite interesting. No one quite knows how that can be there. Kilometers high. And they found evidence, if you believe that little kink here, of what they call aromatic hydrocarbons on the surface, the dark side. It looks as though there are carbon compounds on that side of Iapetus. Hyperion's rather fun, too. And Enceladus, that's perhaps the most interesting. It's got these lovely little cracks on the surface, but they found little jets of water vapor coming out. And we think that beneath the surface, there's a sort of region of pressurized water, kept warm by the tidal heating from below, and these vents are coming out. So they're cold geysers, they're called. So that's a third place where you've got liquid water. And there are interesting chemicals discovered in the vapor. It's not impossible there could be life there as well. A nice view, there we are, of Saturn and Iapetus. Artist's impression, I should say. Titan, of course. There's Titan, seen beyond the rings. You can't see much visually because it's got a thick methane atmosphere and nitrogen. There's a lot of haze in it. That's its size compared to the Earth and the Moon. But Cassini had infrared cameras which could look through the haze and see the surface. But more significantly, it produced a little lander to go down through the thick atmosphere. The atmosphere is a good bit thicker than we have on Earth, and quite high atmospheric pressure as well. So here's the Huygens probe going down to the surface. It went down in a very streaky little way, and in fact radio telescopes will help measure that as it went through the various parts of the atmosphere. on its little parachute there. That's a view from about 10 kilometres up. And this is lovely. Look at this. Do you see these little rivulets coming down to this sort of region here? It looks as though it's sort of water flow. Now, of course, it isn't. And, in fact, they're dry. But this is where we think liquid methane has flowed down to the lower parts of the surface. That methane, as it rains, picks up a lot of those hydrocarbons from the atmosphere, sort of sweeps them out of the atmosphere, and leaves the underside, or the bottoms of these little rivulets, covered with a dark material. So they're dry at the moment, but we do believe they have carried liquid methane in the past. That's just an artist's impression of it landing. And here is another view, and that's the photograph it took. This is all ice, and ice at these temperatures is very, very solid. There was a penetrometer that measured the forces on landing, and it appeared to be a bit like a creme brulee in terms of standing on it, or someone said a cowpat, in the sense that it looked as though there was a sort of a slightly surface crust which was fairly strong, and then beneath that something a bit soggy. Now, it's not impossible that by chance the penetrometer hit a little pebble, a nice pebble, which then moved out of the way. But I think a cowpat's more interesting. So there we go, that's the surface. Now, the most exciting thing perhaps is that radar on Cassini has shown these lakes near the poles of Titan, made of methane. And look at this one. Can you not see the little rivulets that could bring the methane down to the lakes? That's lovely. And I think to confirm that, quite recently, they've got what you call a glint, a specular reflection off the surface of one of those lakes. So this is the only other place in the solar system where we believe we have liquids on the surface. But of course, in this case, methane or possibly ethane. That's probably a heightened view. I don't think it's quite as jagged as that. But it's probably the place in our solar system that looks nearest to Earth, admittedly at a much, much colder temperature. So finally, very quickly, I know time's running out, there is a probe on its way to Pluto and Charon. It will reach there in 2015 and carry on out into what's called the Kuiper Belt. It's called the New Horizons space probe. When it was sent, Pluto was a planet, but as you know, sadly no more. It has, Pluto, a big moon called Charon, two little moons called Nix and Nix and Hydra, forgive me. And from the Earth, the Hubble Space Telescope gets some sort of feel that it's not totally smooth, but really not very exciting. We hope to do better. It was launched in 2006 at a speed of 16.5 kilometers per second. That's fast. That's fast enough to escape the solar system. So instead of having to do multiple gravity assists, it hasn't had to do so many. It went past Jupiter on its way, and its first sighting of Pluto was in 2006. Just two little pictures there. Pluto had moved. It's not an easy thing to see, but it was there. Here it is going past the Jovian system on February 28, 2007, and it did in fact take a wonderful image of Jupiter as it went past, and I think it's rather lovely. Here is Io. Do you see the little plume there from volcano? And look at that little time sequence. So there we have an active volcano taken by New Horizons as it went past, and we're nearly there. Just a few weeks ago, it was halfway there. So it's got a while to go there, but it'll get there in 2015. It will pass the orbit of Uranus in 2011, Neptune 2014, and then 2015 it will fly by Pluto and Charon. And my final thing is to hope that you will come to a lecture given to my successor's successor sometime in 2015 or 2016 to learn about what New Horizons found. Thank you for listening.